Okay, so this is 7.7. We're finishing improper integrals. We're going to cover 7.6 today also. This is just the last example we're going to do. So now, what we're talking about is a comparison test. So comparison test for improper integrals. So we're going to compare it to something that we know. If there's something I don't know, I'm going to do something, I'm going to replace it with something that I do know. So in that whole information is that I have a function, g and f be two functions that are non-negative continuous on the interval from a to infinity. Suppose that f of g is greater than g of x. I'm sorry, f of x is greater than g of x for all numbers where x is greater than c, where c is actually greater than a. What this means is if this converges, if f of x converges, so if the function that's greater is going to converge, then the other one should also converge. If the greater one converges, the one that's less will also converge. Okay? If it diverges, then the other one should also diverge. So proof follows a property definite integrals, the function continuous closed interval, a to b, then blah, blah, blah. Okay, so now, here's what it means. So for this one right here, we're looking at it, and since this is an improper integral, I'm going to say, because of how this is, right here, I'm going to say that I'm going to have negative x squared is going to be less than equal to x. Oh, sorry. No, too soon. Sorry. Too soon. So, starting off, so let's go x squared is going to be greater than equal to x. You guys agree on that? Yeah, that one's pretty straightforward, right? I was jumping too far. So x squared is greater than equal to x. Yeah? For everything, right? Okay, good. So what about if I negate both sides? So negative x squared is going to be less than equal to negative x, isn't it? Yes? Okay, so now we're doing a comparison test. Instead of having the negative x squared, we're now going to compare it with, right here, my negative x. So my comparison should be from here, starting this, I'm replacing it this. So now it's going to be, I have 1 to b, and that's going to be of e to the negative x dx. So I'm taking the limit as b goes to infinity. Did I totally screw up everyone right now? Hopefully not. So we're just checking this to see. So I start off with something that was greater, right? So then the less one should be the same. So now we're doing that here. So that's why I replace it with this. So now if this function right here converges, then my original function should also converge. Yes?
Yes.
No. I'm getting a funny face over here. Hey, B. Okay. All right. So let's go ahead and do this now. So now it's going to be, what's that going to give me? Basically going to use that thing, right?
Negative.
Yeah. So it's going to end up becoming limit as b goes to infinity of my function, which would be negative, right? E to the negative. Come on. I'm running out of ink. Negative x from 1 to b, right? Are we okay? Good. So now start plugging them in. So now this is going to be, so I'm still gonna, haven't taken the limit of it yet, but I'm just putting it back in so it's gonna look negative 1 over e to the b minus negative 1 over e to the 1, right? Yes? It would be e to the negative b, but then I made it positive down in the denominator. Is that okay?
Yeah.
Okay, good. So now, let's take a look at this. So now from this, we know negative 1 over, okay, what's this going to give me? So as my denominator, as I plug in infinity for my b, as the limit as b goes to infinity, what is my denominator going to end up becoming? Goes to infinity, right? So 1 over infinity is 0. So this is going to give me 0 minus a negative 1 over e, right? So it's going to give me just 1 over e. And is that going to be convergent or divergent? Convergent, because it goes to a number, right? So using comparison tests, I now compared it to something that was convergent. So if this is convergent, then the other also has to be convergent. Does that make sense? Yes? Okay. All right. I think that was the last example. Yeah, okay.